Hi guys, it's Mrs. Rodenwald. Hope you're doing well. Sorry I can't be with you today. Hopefully you'll get what you need to about Hess's Law out of this video. Just a couple of reminders. You have a lab tomorrow. So pre-lab's due at 8:50 tomorrow morning. There is a short video to watch with it that I can't say is the most exciting, but I can say that it does provide some very important information about doing a titration that'll help you and your group be successful tomorrow. So that's happening tomorrow. Today we're going to talk about the first method of using thermochemical data to find heats of reaction. And we're going to split this up into two, mostly because I'm gone today. I've done it in 2 days in the past. I've done it in 1 day in the past. And I just think it'll be easier to just deal with Hess's Law today and come back and talk heats of formation on Wednesday. So that's what we'll do. So I'll adjust your homework a little bit. My suggestion in watching this would be to watch the first two examples is the first video. You'll notice I posted 2 videos. The first one is the first 2 examples, so really the front page. So I'll go through the front page on the first video, and if you feel like you are in good shape and can go with it, then I would go with it, and just do your best to, see if you can get the right answers, etc. for the third and fourth example. If you don't get the right answer when you try the third and fourth example, then please watch the videos, because maybe you're missing something. Maybe you need, maybe you missed something in the first couple examples, or maybe there was something in the third and fourth ones that is important. If you feel like you're someone who needs a lot of examples, that's good for you, then I would just watch both and get all of the notes into your onto your sheet and follow along. So we'll start by talking about, this is what we're doing today. From other known reactions, we're going to look at this part. Wednesday, we'll talk about using heats of formation. This is what we are going to discuss as Hess's Law, which is basically we can use known reactions to figure out the delta H of an unknown reaction. Just a reminder of delta H, change of enthalpy, which is basically heat of reaction. So we talked last week about heat going in, heat coming out, exo-endothermic reactions, talked about enthalpy diagrams, looked at how do we experimentally calculate it. Now we're going to talk about how do we use data to calculate it. So just a couple of reminders from last week. If we are given a fake reaction, you see this fake reaction here, A plus 2B goes to C plus 3D with a delta H. Given that fake reaction, it says find delta H for these things. So let's figure out what we're doing to that first reaction to get the resulting one. So the first one says 3A plus 6B goes to 3C plus 9D. So what did I do to this given reaction? Well, I multiplied it by 3 to get that. Because if we took out the 3, we get our original reaction. So what I'm going to do to my delta H is take 3 times my negative 155 kilojoules to get my new delta H. So I'm going to take 3 times negative 155, and I'm going to get negative 465. Remember, it's an extensive property, so whatever we do to the delta H, or to the reaction, we do the same thing to the delta H. In this second one, the second one says C plus 3D goes to A plus 2B. Well, what did we do there? We just flipped it around. Today we're going to talk about flipping it around being like multiplying it by a negative. So if I flip it back around, I get my original reaction again. And so I just flipped the sign. I flipped it around. That's like multiplying the reaction by a negative. I flipped the sign of my delta H. So I get plus 155. Check that out. I didn't even need my calculator. That was awesome. With the third one, 1/2 C plus 3 halves D goes to 1 half A plus B. Well, I did two things there. I flipped it around, so it's like multiplying it by a negative, and I cut the coefficients in half. So it was like multiplying the equation by negative 1 half. If I flipped it back around, I would get, and multiplied it by a half, I would get, again, my original equation back. So I'm going to take my delta H, multiply it by negative 1 half. That's going to make it a positive, and it's going to cut the delta H in half to be 77.5 kilojoules. So reminder, extensive property, if we flip it around, we flip the sign of the delta H. Keep those things in mind today. Because enthalpy is a state function, which we mentioned briefly last week, we can do this. Because it doesn't matter the steps we take to get there. It matters the change in enthalpy isn't going to be different regardless of how we get there. So we'll start in one place and we'll end in a place, and the delta H will be the same regardless of if we do it in a direct step or we do it in 10 steps. Which brings us to Hess's law. Hess's law says if a reaction is carried out in a series of steps, then delta H for the reaction will equal the sum of the enthalpy changes for the individual reaction steps. Okay, so we're going to look at an unknown equation where we don't know the delta H, and we're going to try to build it from known thermochemical equations. So the first example is fake. Again, 2A plus 3D goes to 2J. You'd be hard-pressed to even find a J anywhere on the periodic table because there isn't one. But 2A plus 3D goes to 2J. So we're going to try to build this equation from data that we're given. So really, you can say it says calculate delta H. So we want to know the delta H for this reaction. So we have two pieces of data. So what we're going to do in order to solve these problems, the first thing we're going to do is look for the first component of the unknown reaction. We're going to look for A in our two known reactions. I find it right here in the first one. I don't find it in the second one, and that's important. So I found it in one reaction, and I'm going to ask myself two questions. Is it on the correct side? And is the coefficient correct? So I'm always going to ask myself those two questions when dealing with known thermochemical equations. So I see that A, according to the reaction I'm looking for, the A is on the correct side. It's a reactant in the unknown equation. It's a reactant in this one. Does it have the correct coefficient? No. It needs a 2 in the unknown. So we're going to multiply it by 2. Whatever we do to the equation, we do to the delta H. I'm going to go ahead and rewrite that equation. 2A plus 2D goes to 2E. Delta H equals negative 100 kilojoules. And I'm going to put a line over that tens place so we know that's a significant 0. All right. So we've doubled it, doubles the delta H. That's what we've done with that, with the A component. So now we look for D, and interestingly enough, I find D in both. I'm going to ignore D, and that's important because we're not going to deal with D in both right now. So I'm going to go on to J. J is only in the second one. So I find J, and I'm going to ask myself those same two questions. Is it on the correct side? No. So I know I'm going to have to flip it around, which means I'm going to have to flip the sign of my delta H. Does it have the correct coefficient? Yes. It's a 2 in the unknown. It's a 2 in the known. So I don't have to multiply it by any other factor than 1. So now I'm going to flip that around and get D plus 2E goes to 2J. And then I'm going to flip my delta H plus 72 kilojoules. And so then I'm going to add up my equation. So I'm going to take and say, okay, I have 2A plus 2D plus D plus 2E as reactants. So everything on this reactant side ends up here. And then I have 2E plus 2J on my product side. Everything on my product side ends up here. Now I'm going to cancel out things that are exactly the same on both sides, if there are any. 2E and 2E. 2E on the left, 2E on the right. We just get rid of that. If they were different numbers on opposite sides, I would subtract them. Then we add together anything that's the same on the same side. I have 2D and a D. That's going to add together to give me 3D, which leaves me with 2A plus 3D gives me 2J. Is that the reaction that I was hoping to make? It is. I made the reaction successfully. So then I'm just going to add up my delta H's. Remember, Hess's law says it'll equal the sum of the enthalpy changes for the individual steps. I use 2 steps to build my reaction. That gives me a delta H of negative 28 kilojoules. Negative 28 kilojoules. If we kept that only that tens place of significance, that would be negative 30 kilojoules. And I am finished. Successfully made that reaction from the known reactions. So let's do some real chemistry. Let's look at that second one. Iron 3 oxide reacts with carbon monoxide to form iron and carbon dioxide. So I have a couple known reactions. We're looking for the delta H of reaction of that one. So first thing we're going to do is look for Fe2O3 as a solid. We find it in the first one. We don't see it in the second one. We ask our 2 questions. Is it on the correct side? No. So I know I need a negative. Does it have the correct coefficient? Yes. So it's just going to be a -1. I'm going to rewrite it, flipped around, Fe2O3, 2Fe, and you might wonder why I left all that space. I like to keep my arrows consistent where they are, just because I think it makes it easier for me to see what are products, what are reactants. So I just think I'll need extra room over there. Maybe I will, maybe I won't, but I just did it that way. Delta H is going to be positive 822.16 kilojoules. Now I'm going to look for the CO as a gas, not in the first one. I see it in the second one. Is it on the correct side? Yes. Does it have the correct coefficient? No. I need to multiply it by a factor of 3 in order to get the correct coefficient. So I'm going to rewrite it as I multiplied it. 3 COs plus 1/2, oh, not 1/2, 3/2 O2 goes to 3 CO2s. Now I've used both reactions. Most of the time then we can figure we're done if we did it all right. I'm going to multiply that 283 by 3 and I get negative 849 kilojoules. So let's just see if we've added up our reaction correctly. Those 3/2 O2s cancel, and I do that up above sometimes just to make sure. But they cancel, and I make sure my other components are there. And they are, and that's all that's there, which is important. I get that. that's the reaction that I was looking for. So I've just built that reaction from my given reactions. So now all I'm going to do is add up my delta H's. When I add those together, I get negative 26.84. I've got a hundredths place here. I've got a tenths place here. So I want a tenths place here. Negative 26.8 kilojoules. And there's our answer. All right, so again, I'm going to stop there, and that's going to be the first video. If you feel like you understand what you're doing and want to run with it, great. If not, I go through the other two examples next. The answers are on the board for you for those other two examples, so if you try them and you get them, then I wouldn't worry about it. If you try them and you don't get them, I would watch that example and make sure you understand it. Otherwise, hope you guys have a good rest of your day. Looking forward to lab tomorrow.